Right, yesterday you had a worksheet dealt with just upper sum, lower sum. We had to deal with local max and local min during those also. We talked about yesterday, you had negative area, you have positive areas that you had to worry about. You're not always going to be in an endpoint at an of a subinterval. When you have a local max or a local min, you're not always going to be an endpoint of the subinterval, where before, when we had a very basic fundamental one, it was always going to be at an endpoint with respect to your height. So you had little different things that were thrown at you, questions you have on anything upper and lower sum. Okay, solutions were provided for you. Once again, when you're dealing with the upper and lower sum, you have to have a graph. Okay, because you don't know where your local max and local mins are going to be. You don't know what side of the graph that you have to look at, what subinterval you can, or side endpoint of the subinterval you have to look at. So you have to worry about the graph, and you have to work with the graph. What we're going to talk about today is 4 different types of sums that basically we can utilize our subintervals to be able to calculate these sums. Once again, we're dealing with approximations. Now, I'm dealing with approximations, and I'm going to give you approximations so we can get through the idea of what we mean by calculations of approximations. I'm not going to make my subintervals very small because it takes time to go through subintervals that are a quarter or a half or a tenth. But knowing that you can be able to calculate your subintervals that are smaller, you can calculate those upper and lower sums, or the sums that we go through today. Once again, this will be a little bit nicer for you because we have 4 different sums to deal with today. We have a left sum, right sum, midpoint sum, and a trapezoid sum. 4 different types of sums. Once again, the upper and lower sum were 2 boundary values that you can have with the actual area. Your upper sum was one approximation, the lower sum was another approximation, and we know the actual area is somewhere between the upper and lower sum. Okay, the next 2, the left sum and right sum, we're going to be in the same boat. These are going to be 2 boundary values. We know the actual area will be somewhere between these 2 boundary values. We don't know where, but as delta x gets smaller, we get closer and closer and we squeeze in on the actual area. So if we take a look at the left sum, once again, these sums today will be a lot easier because we can just use subintervals. We don't have to have a picture here. We'll still go through the picture, but you can just work with basically the subintervals. The nice thing about this also is I gave you partial definitions already. So you don't have to do the entire definition. Okay, the left sum, Riemann sum of rectangles created by the partition lines, the x-axis and the horizontal line drawn intersecting the graph at the left-hand side of the subinterval. So we are now dealing with the left-hand side of the subinterval. We're still dealing with the same function. F of x equals x squared plus 1. We're going to still deal with an interval from x is a member of, what do we do, -1 to 3. That was our subinterval, correct? That we worked in the previous one. So we're still dealing with the interval from -1 to 3. And we're going to still deal with a delta x is equal to a value of 1. So we're going to go very basic with this. We're not going to go huge amounts of delta x's. So our subintervals are still going to be the same. -1 to 0, 0 to 1, 1 to 2, and 2 to 3. So we still have our same subintervals that we've been working with. And I still have a graph there. And we'll still look at the idea of the graph. We're still going to draw vertical lines at our partition values. That's going to be the same. But now the difference is going to be you have an intersection point, and that intersection point with your graph is going to be at the left-hand side of the subinterval. Which, if I just look at my subintervals, I'm going to draw from -1, 0, 1, and 2. So from -1, I'm drawing over. From 0, I'm drawing over. From 1, I'm drawing over. And 2, I'm drawing over. Which we don't need a graph to see this. We could just look at the subintervals here and know that our height is going to come from the left-hand side of the subinterval. So we have areas 1, 2, and 3, and 4. Area 1, we still have a base of 1. We're still creating a rectangle here between the x-axis. We're still calculating areas of rectangles. But our height is going to be our function value at -1, which we know is a value of 2. Then our A2 is our base is going to be still a value of 1. But our height is going to be our function value at 0, the left-hand side of our subinterval. So once again, do I need a picture there? No, I can just look here, and these will give us our heights. So we have 1 times the value 1, which is a value 1. Our A3 will be 1 times our function value at 1, which is 1 times 2, a 2, and our A4 is going to be 1 times our function value at 2. So we have 1 times 5, or value of 5. So our left sum, we just add up our values here. We have 2 plus 1 plus 2 plus the value of 5. So we have 10 squares. So this would be our left sum. We can also deal with the right sum, which is the exact same definition that we just wrote down up top. But now, we just have the right. So it's a line drawn intersecting the graph at the right-hand side of the subinterval. Once again, we are doing the exact same -1 to 3, delta x is equal to 1. Our subintervals are still going to be the same. -1 to 0, 0 to 1, 1 to 2, and 2 to 3. we can get a visual picture of this to begin with. But once again, this visual picture is basically for explanation and to show, but ultimately, we're now looking at the right-hand side of the subinterval. So we are utilizing the values 0, 1, 2, and 3. So our rectangles are going to come from 0, 1, whoopsie. 2 and 3. And we don't need a picture to show us what side we're drawing it from, because with the right sum, we're using the height now as our function value at 0, 1, 2, and 3, the right-hand side of the subinterval. So A1 is 1 times f at 0, A2 is 1 times f at 1. So we have 1 times 1, 1 times 2. A3 is going to be 1 times f at 2, which is 1 times 5, and A4 is 1 times f at 3, which is 1 times 10, which is a value of 10. So we can add these up, 1 plus 2 plus 5 plus 10. So we get 17, 18 squares. And we don't need the picture. We can just look at our subintervals. We can just use our height. Our height is going to be just that function value at the right-hand side of our subintervals. But we can also use these as we can utilize these as boundary values, and we can actually say our actual area is going to be somewhere between our left sum and right sum. And we might have to flip the right sum and left sum. Because what we have here is we have approximations, but these gives us boundary values to the actual area. And if we take a look at the picture, if we take, like for the right sum, we have an under approximation here, but we have 3 over approximations. So this would probably be a little bit more of an over approximation. If we look at a left sum, we're over here, but we have 3 under approximations of the areas. So we have under and over with our approximations. But once again, these are boundary values that we can utilize to be able to calculate or to estimate the actual area. And if we shrunk our delta x down, these values would get closer and closer and closer together. Midpoint sum. Midpoint sum. Once again, we're dealing with a midpoint sum. These midpoint sum, along with the left and right hand sum, can be utilized. We can utilize our subintervals to be able to calculate this. We don't need a picture. We'll show the visual up here, but we don't really need the visual. So we have the Riemann sum. Rectangles created by the partition lines, x-axis, horizontal axis, horizontal line drawn intersecting the graph at the midpoint of the subintervals. Now what we're going to look at is at the midpoint of the subintervals. So it's the exact same definition. Left sum, we use the left-hand side of the subinterval. Right sum, we use the right-hand side of the subinterval. Midpoint sum, we now use the midpoints of the subintervals. So if I look at my subintervals, we still have x to the member of -1 to 3. Our subintervals, x to the member of -1 to 0, 0 to 1, 1 to 2, and 2 to 3. We still have our partition lines. Draw horizontal line, vertical lines at the partitions. But now what we're utilizing is we're going to utilize the midpoint, which is -0.5, 0.5, 1.5, and 2.5. So at our midpoint of our subintervals, we're going to draw our horizontal lines. Oopsie, that was bad. So we still have our 4 areas. So area 1 is going to be our base, which is a value 1, times our height is going to be at -0.5. A2 is going to be 1 times our function value at 0.5, which is our midpoint. And once again, we can look at the graph here as a visual, but really, we just need our subintervals. A3 is 1 times our function value at 1.5, and A4 is 1 times our function value at 2.5. So now, once again, this is where your calculator comes in handy. We have in our function values f of x equals x squared plus 1 as our y1. We can now calculate, well, what's our function value at 0.5, at -0.5? Well, we're squaring 0.5, which is 0.25 plus times 1. So we have 0.25 here. Then we have 1.5, which is squared 2.25. So we have 1 times 2.25. And then 2.5 squared is 6.25.
Each one would be have 1 on it.
Oh, I forgot to add 1. My bad. So we have 1, 1. So we have 3.25 and 7.25. My bad. So we can do our Riemann sum. And add them up. So if we add these up, we get 13. Which now, with the left and right hand sum, we have boundary values. With the upper and lower sum, we have boundary values. With the midpoint sum, we don't have a boundary value. It's, believe it or not, a pretty good approximation. Because if we take a look at each subinterval, let's see, I'm over here, but I'm under here. I'm over here, but I'm under here. So if I take a look at these triangles or curved triangles, they sort of cancel each other out with the over and under approximations. So 13 is an actual, not a bad value. And when we do the actual calculations of this, this is going to be pretty close. And once again, you get delta x a little bit smaller, it's going to narrow down to the actual value pretty good. Last one. Last one, trapezoid sum. The return of the zoids. The zoids. I like the zoids. There should be a some sort of science movie. Some, aliens come in. And it's going to be called The Return of the Zoids. They have trapezoid heads. It's sort of tilted upwards. Parallel here, but you got to tilt upwards. We create trapezoids. We create, hopefully, these zoids. Okay, the Riemann sum of trapezoids created by the partition lines. Okay, it's still the same. The x-axis still the same. And a line drawn from the intersection point of the partition lines in the graph of the function. This also is a pretty good approximation. Because if you remember back to local linearization, we have curved lines that we were trying to linearize, make them a line. That's what this is sort of using. We're linearizing our curve. Starts out the same. We got our partition lines. We have our x-axis. Very similar to what we've been dealing with, okay? Start out like this, but now the difference is we draw a line from the intersecting points of our graphs. So we draw a line here, we draw a line here, we draw a line here, and we draw a line here. And we calculate the area of the zoids. Which, if we take a look at the area of the zoids here, it's going to be pretty close. And if you shrink down delta x and get smaller with your delta x, this is going to get even better. You're linearizing a curve. But we have to remember, how do we calculate the area of a zoid? The area of a zoid! How do we calculate the area of the zoids? Do we remember? Oh boy. Come on, rattle ahead a little bit. Well, what we have to remember is the definition of a zoid. Trapezoid. It's a quadrilateral. With one pair of parallel sides. One pair of parallel sides. Trapezoids are quadrilateral with one pair of parallel sides. Well, if I take a look, our vertical lines that we draw is the parallel sides. Parallel sides. They're called the bases of the zoids. So your two parallel sides are called the bases. Okay? Those are called the bases, which is going to be a little bit different for us when we calculate the area here, because what we've called so far, we've said this is our base, this is our height. This is our base, this is our height. Base, height. That's what we call it. Well, now we're going to flip that around. These here are going to be your bases. These here are going to be your bases because they are the parallel sides. The height is the perpendicular distance between the bases. Okay, we are kicking ourselves back into our freshman or sophomore years whenever we took geometry. And we defined, when we were working with quadrilaterals in geometry, and we defined all kinds of different types of quadrilaterals. We had squares, we had rectangles, okay, we had trapezoids, and we had rhombuses. Okay, so we're kicking back into that and into our memory. So when are we ever going to use this again? Well, we're using it again. How we calculate the area of a zoid. Is we take base 1 plus base 2 divided by 2 times our height. Or this could be 1/2 B1 plus B2 times our height. Those are the two formulas that you'll see. What I like to utilize, because when I taught geometry years and years and years ago, I tried to keep it all in the same mental aspect of how we calculate the areas: base times height, base times height, base times height, base times height. Whether it was a rectangle, triangle, didn't matter. But when we talk about the zoid, I said it's your average base. It's your average base. Well, how do you take the average of, two sides that are your bases? How you take your average, you add those two together, divide by 2. So if we look at area 1, we have to take the average as our base. Well, our bases are at -1 and 0. Our function value at -1 plus our function value at 0. I take the average of them and multiply it by my height, which is a value of 1. My distance between the two bases, my perpendicular distance between the two bases. So we have our function value at -1, which is 2, plus 1 divided by 2, which is 3/2. Then our A2 is our function value at 0 plus our function value at 1 divided by 2 times our height. So we have 1 plus 2 divided by 2, so we have another 3/2 in there.
A3, our function value at 1 plus our function value at 2, divided by 2 times our height. Our function value at 1 is 1 plus 1, which is 2. Function value at 2 is a value of 5. So we have 5 plus 2, 7 2ths. And our A4 is our function value at 2 plus our function value at 3 times the value of 1. So we have 5 plus 10 divided by 2 times the value of 1. So we have 15 2ths. So we can add up all of our 2ths. So we have 3 plus 3, that's 6, plus 7, 13, plus 15 is 28 over 2, which is 14 squares.
Is this the most accurate one?
This is probably your most accurate. This is a very good approximation. Okay? And once again, you shrink down delta x, it's going to get smaller, it's going to get better and better and better. Okay? Now, once again, do we really need a picture? No. Because if I take a look, my subintervals here's our subintervals. My bases, I'm using both of these values, -1 and 0. Then we're using 0 and 1, 0 and 1. Then we use 1 and 2, 1 and 2. Then we use 2 and 3. So I can look at our subintervals to be able to find the heights or the bases, basically the distance of the bases. So everything that we do here, that we did today, you don't really need a graph for. But what I will do, I will write down my subintervals. Okay? What my subintervals are. And then I will just refer back to my subintervals. Am I doing the left sum? So I'm just using my left-hand side. Am I using the right sum? So I'm just using the right-hand side. Okay? Or am I using my midpoint? So I'm finding my midpoint for each one of these. Okay? Or if I'm using a trapezoid, I'm using both of my endpoints to be able to calculate the average of the two bases. Okay? So you can use your subintervals to be able to deal with your calculations. Okay? A lot easier than looking at a graph. Alright? Questions? Alright, I got a worksheet. It is exactly the same worksheet that we did yesterday for today. The exact same worksheet from yesterday to today, except for now, you're dealing with left sum, right sum, midpoint sum, and the return of the slice sum. So for your media project, your final media project that you have from Mrs. Ed, you're in media, and you have to create a movie. You can name it in Return of the Sillies.
I got you, Mr. Gregory, don't worry.
Alright. Solutions are posted for you, and the rest of the time is yours.